Hello everyone, I'm Xie from Medicine. Today I will introduce our work on accelerating mobile web loading using cellular information. Web latency is very important. Amazon found that every 100 milliseconds of web latency causes a 1% in sales. However, even under the high-speed wireless access, mobile web performance nowadays is still unsatisfactory. For example, over 4G LTE networks, the average downlink speed is around 12 Mbps, and the typical mobile web sites via site visible, so it's below 12 Mbps. So one would assume the web loading should finish in 1 second. However, in practice, it still takes 2 to 9 seconds to load the web page over LTE networks. The root cause of this poor performance is a poor interaction between mobile web traffic, which has a light and burst pattern, and TCP slow start, which is designed for long-lived load, and LTE cellular network, which has high round-trip time. The poor interaction between these three layers leads to severe bandwidth underutilization. Let's look at this problem in more detail. So TCP slow start, it gradually increases the sending rate. So every time the link receives an acknowledged packet from the remote peer, that design is good for long-lived loads, like when they stream a video or download a live file. It will finally convert to the network bandwidth. But that performs poorly for the short-lived web session, because the small amount of traffic load will lead to a small amount of acknowledged packets, and finally, the sluggish bandwidth provision. If we look at the TCP sending rate in cycle-band, we can see it takes some time to convert to the available network bandwidth, but web loading session finished well before that. So the during this web loading is well below the available network bandwidth. Meanwhile, the high round-trip time of the cellular link also slows down bandwidth provision. Because of the high round-trip time, the ATK packets from the remote peer will be delayed, and that will also slow down the exploration of the bandwidth. Here we show the web loading instance over the wireline network with low round-trip time and the LTE network with high round-trip time. We can see the high round-trip time of LTE network severely slow down bandwidth exploration, because it must wait for one round-trip time for the ATK from other side to arrive. Every time before it can increase its sending rate. So the key challenge to accelerate mobile web loading is to accelerate the bandwidth conversion. To do that, we have two key observations. The first is the bandwidth exploration should no longer be bounded by the amount and latency of acknowledgement packets. The second observation is the cellular link is typically the network bottleneck. Based on these observations, we propose our solution, cellular link aware web work flow. It replaces the sluggish TCP bandwidth exploration with a more efficient mechanism that converts to the bandwidth much quicker with the assist of the cellular link information. Our design consists of three design components. First, we have the cellular load analyzer, which monitors the resource utilization on the physical channel. It then feeds this information to the Cellular-Informed rate control, which adapts the HTTP traffic rate from the web server physical layer statistics readily available on commodity phones. Basically, we propose the first and the latest model that can compute the cell-wide resource utilization based on RSRQ. So I will introduce this in more detail. If we look at the physical channel spectrum of LTE, we can see the base station it keeps sending the reference signal. Meanwhile, it allocates the spectrum to data transmission based on the traffic load. And the RSRQ is defined as the power of the reference signal divided by the total power, or the sum of the reference signal power and the data signal power. If we compare the RSRQ value, then we will know the ratio between the data signal power and the reference signal power, which is exactly the ratio between the resource amount allocated for data transmission versus the resource allocated for reference signal. In the LTE standard, the resource allocated to the reference signal is predefined. So based on that, we can directly estimate the resource utilization for data transmission. To validate this model, we measure the RSRQ and the resource utilization over real-world commercial LTE networks and compare it with the theoretic curve computed based on this model. And we can see the measurement matches the model very well. After getting the cell-wide resource utilization, the cell load monitor will feed into the Cellular-Informed grid control module, which can then estimate the amount of unused resources over the channel. Meanwhile, from the phone's diagnostic interface, we can also get the amount of resources allocated to the user itself. By combining these two, we will know the amount of totally available resources. Then, based on current channel conditions, we can map it to the available potential network bandwidth. In contrast, existing works like secret, it also knows the physical layer information, but only the amount of resource allocated to the user itself is unaware of the amount of unused resources, thus cannot fully explore the network bandwidth. Our rate control module also does a fairness control, so we design a hybrid bandwidth separation algorithm which allows it to fall back to conventional TCP when it detects no resource available, so it won't get stuck. Meanwhile, it can accurately throttle the sending rate when it finds the base station allocate this resource to itself to avoid congestion. For example, if we already have a cellular link saturated by an existing flow user, for the new user joining this network, it will detect no available resource to explore, and then it will fall back to conventional TCP and perform conventional slow start. Meanwhile, the existing user will detect this amount of resource allocated to itself and actively throttle its rate, and then also fall back to conventional TCP. In this way, our algorithm is designed to be TCP friendly. Our above design assumes cellular downlink is a network bottleneck, but in practice, it may not always be that way. So we have the network bottleneck detector to handle this. The basic workflow is like this. First, the client will monitor the cellular downlink channel for the available resources and ask the server to speed up and fully utilize this resource. However, if the resource utilization do not change, then we know the actual traffic must be jammed somewhere on the VLAN part. So in this case, we will fall back to conventional TCP to guarantee the fairness. We implement a real-time test for our system for evaluation. At the client side, we use the phone diagnostic interface to extract the physical layer statistics like RSRQ and channel quantity, which are to cache the kernel to implement our algorithm. And the server uses an RH2 HTTP server to send the web traffic to our client. In the evaluation, we first validate our cellular load analyzer. So we let the client receive an I-curve TCP stream which has a traffic rate increasing linearly by 0.5 Mbps per second. And we record the traffic rate and the resource utilization monitor by our system. You can see these two curves match very well, which means our cellular load analyzer can track the cellular resource utilization in real time. Then we perform the system level evaluation by comparing the page loading time with conventional TCP, like TCP cubic and the TCP Vegas. Also the state-of-the-art solutions like Secret from Go and Verus. We test all these algorithms over popular websites like Apple and LinkedIn. So from these results, we can see our algorithm reduce the page loading time by around 30% over benchmark algorithms. We also performed a lot of experiments over a wide range of network conditions, including different background traffic load, different channel quality, different mobility levels, different phone models, different cellular operators, and a different version of HTTP. You can see in all these cases, our algorithm outperforms existing solutions. So in conclusion, mobile web performance is sluggish nowadays, and because TCP converts to the available network bandwidth slowly. To solve this problem, we propose flow or cellular link layer there, which leverage the physical layer information to accelerate the bandwidth convergence. In this way, it reduces the page loading latency by more than 30% over conventional TCP, and it requires no hardware modification to convert it to phones. And finally, it's carefully designed to be